Hello, everyone. It's me, Mr. Younger. I'm here teaching conceptual physics and thought I'd go over a few examples from what we call Chapter 2 in the 13th edition of Hewitt's Conceptual Physics. That's specifically on Newton's first law of motion dash inertia. So this video is basically just me showing you specific examples and how to work them, how to figure out what their answers are. So let's begin by sharing my iPad screen. It should be coming up any second now. So the first question we have here is if gravity between the Earth and the Moon suddenly vanished, the Moon would continue moving in. This is just a typical example that we would ask you. Normally, it would have like a multiple choice type answer, but I'm at least on my test. But in this case, I'm actually asking for an open-ended response because I want to give you guys an open-ended response. So uh, basically what's going on is when an object is in orbit, for instance, around the Earth, which is what the moon is doing, then you could imagine that this is the path it's following. The important thing to understand, of course, is that the Earth is roughly at the center. Now, I've tried to draw this at the center, but it's not necessarily going to be exactly in the center, and it seems like I'm not even going to be able to straighten it up and center it up more because it won't let me move. There you go. Now I can move it. So this looks a little closer to the center. That's pretty good. And that's supposed to be Earth. And this is clearly not the scale as those of you who are familiar with this, are familiar with astronomy, know that basically the moon orbits about 60 Earth radii from the center of the Earth. And of course, the Earth's radius is exactly one Earth radii. But the important point is to realize that if the moon is right here, then at that point, its velocity is pointing this way. We call that tangential. Well, we did call that tangential, but it became something different. There. Now it's tangential. So notice we're trying to make a arrow that is in fact exactly parallel to the surface or to the edge of the path that the Earth, or excuse me, that the moon is following. So this blue line is the orbit of it's the orbit of the moon. So that's sort of the path it's following, if you will. And of course, this is the Earth, which hopefully you already figured that out. But at that particular point in time that we've got drawn there to the right, if the gravity was instantly turned off, like the Earth instantly disappeared, and gravity that was originally causing the moon to orbit the Earth, if that disappeared, then and it happened at this second, then the actual moon would continue going off in this direction. If, however, the moon was right here at the time then that happened, then it would continue to go off in this direction. These paths are called tangential, or these vectors are called tangential to the orbit. So these are what we call tangent lines, and that just, like I said, means parallel. So you can see that I'm trying to draw arrows that are parallel to the actual part of the orbit that the moon is at a given drawing. I'll draw another one here, and at that point, the tangential velocity points this way. And if gravity was turned off there, then the moon would tend to continue off in that direction. Notice they're not going off in circular lines or anything like that. They're actually leaving in straight lines because Newton's first law of motion says that an object in motion tends to stay in that state of motion unless acted upon by a net external force. And the net external force in this case would have been gravity, and that would have been the only force, but we turned it off. So it went from one that was orbiting to one that was just going at constant velocity. And as I pointed out, the velocity of the actual moon at each of these three locations is more or less represented by that black arrow. In other words, it's tangential again to the actual orbit itself at the point in time when you consider releasing the gravity. Then it's going to continue going in that straight line as the purple dashed lines show. Hopefully that explains that. Whirl a rock at the end of a string and it follows a circular path. If the string breaks, the rock will. This is a very similar problem to the last one. In fact, I'm going to use almost an exactly the same diagram. I'm going to allow my note-taking program to make a good circle out of my crappy circles. So in this case, we're just talking about a string with a rock in it on the end of it. So we could imagine, for instance, that the rock is right here. And then with the rock being right there, that means its tangential velocity is that. And we look at, for instance, the string going this way. So that's our little string. Actually, I'll tell you what, I'll just make the string in red. So there's the string. If the string were to break at that instant, then the rock would continue to go off in this straight line. If the rock were to, or excuse me, if the string were to break off right here at the peak, at the top, then the tangential velocity there is that direction. And that would mean that if we broke the string right there, it would follow off in this direction. So again, there's a string. If, on the other hand, we had, let's say, the string here and the rock was right here, at that instant, tangential is in this direction. And in that case, again, the rock would leave in a straight line parallel to the velocity it had at the instant the string was cut. So in all these cases, we basically see that the object that is doing the circling continues to travel in a straight line parallel to the path it was following at the instant the force disappeared. So again, these tangential diagrams are hopefully helpful. Uh, let's try another question, another example. If your car runs out of fuel while driving, the engine stops. You don't instantly come to a stop due to, and this is a little open-ended question, but what they're looking for specifically here is the idea that inertia is what keeps the object moving. So even though we sort of tend to think accidentally in Aristotelian terms, Aristotle taught us that objects had to have a force to require them to move unless they were under natural motion. And in this case, this is not natural motion. We're just imagining a car driving down the road. It's even hard to figure out exactly what parts of the four or five elements that Aristotle came up with that the car is made out of. So that's a little bit of a problem, but we know it's moving horizontally. That would be violent motion, and under Aristotle's rules, that would mean it needed a force to sustain that motion. But after Galileo came along and ran his experiments with inclined planes, he discovered that actually an object tends to stay in its state of motion, which most succinctly can be said by saying the velocity is a constant. If that velocity happened to be zero, then it's going to stay zero. But if that velocity happened to be 32 miles per hour at 15 degrees east of north, then it's going to continue being 32 miles per hour at 15 degrees east of north. And all of this is because, according to Galileo, is because of inertia. Now, again, inertia is just the word we use to explain the tendency of matter to be kind of lazy about changing. So it doesn't necessarily answer the question, it just tells us that that's the way things behave. Uh, let's try the next one. Tension is a force that tends to, and then again, both of these questions would be a lot easier to answer in terms of multiple choice questions. But in this case, I'm trying to give you a an open-ended response so that you can better understand exactly what tension is in this case, and in the other case, what inertia is. So tension is a force that tends to stretch objects. So we normally talk about tension being in ropes, but we also talk about tension being in 2x4s and 2x6s and 2x8s. But they also are occasionally, in the cases of 2x4s and 2x6s and 2x8s, those are also occasionally in compression, whereas a string could never really be in compression unless it was perhaps frozen solid or something, meaning you took a string and you stretched it and you sprayed water over it, let it freeze, and then it would become more or less a solid, and then you could apply force at each end trying to compress it. But that would not be tension, that would be compression. So tension is a force that tends to stretch an object. That's really the best definition we have for it. So tension is a force that tends to stretch the object that the tension is on slash applied to. I should also say tension, that N came out a little bad there. So tension acts parallel to the object it is applied to. And what I mean by that is, for instance, if you put a 2x4 in tension, and this is a case where I should be drawing this with the aid of the program, maybe, like that, then the tension has to be actually parallel to the beam, like that. This is a good place to pause because my nephew's getting ready to come in and my dogs are going to bark. Uh, let's pause for a second. All right, now I'm back. So here's our next question. When field physics hangs at rest in the middle of the clothesline, the tension will not be the same in each side of the rope when, and they're asking you for specific cases. Again, this is a type of question that would probably be better served as a multiple choice, but I want to open up in a open-ended fashion. So if we want to try to imagine a clothesline, generally speaking, the clothesline would be just a straight rope like this. We could say it would be tied to a pole there. It would be tied to a pole there. That's basically just a rod going into the page. And then, of course, it would have a vertical pole that would hold it up above the ground. But that's what a clothesline looks like. If we actually had a person hang from the middle, then the symmetry would mean that the rope on this side and the rope on this other side would actually be at exactly the same angle. Meaning, if I measured from, let's say, vertical to this side and got, let's say, 72 degrees, then this side would also be 72 degrees. And what we'd have is a tension in this rope that, again, since it's a tension, it's going to be parallel to the rope. And then we'd have another tension in this rope like this. And by symmetry, the fact that the left-hand side is a mirror image of the right-hand side, meaning if I just replace that purple line there with an actual vertical mirror and I stepped off to the left and looked, it would look exactly the same, even though I'm seeing a mirror image of the right-hand side instead of the actual right-hand side. That is a symmetry. And because of that symmetry, there's no way we could expect the left hand tension or the right hand tension to be a difference in magnitude, even though my drawing seems to suggest they are slightly differently, having different magnitudes. But that's just a boo boo by me. The main thing is to remember that in order for the person to hang, uh, Phil Physics, for instance, in order for him to hang, those two tensions have to counteract his weight, which would be weight is equal to mg, like that. Now, in order for this to be an equilibrium situation, which is really what we're talking about here, we know the summation of the forces has to equal zero, which is a innately vector concept. And what we have to do is realize that whatever this tension or whatever this weight is, those two red forces must add to give exactly the opposite. Now, I drew this force a little too big for the weight, so I'm going to shorten it a little bit to make it a little more reasonable. So now let's say this is the weight, and I'll say W is equal to mg, like that. And I can get rid of this. Now, if I want to imagine the opposite of that, which would be what we call the equilibriant, meaning if I just had the force W equals mg pointing down, and I wanted to know what force would cancel out that force would be called the equilibriant. What force would cancel out just the weight? I'm not counting the tensions, but by necessity, if the two tensions add up to be the equilibriant, then we have a equilibrium situation. So what we know is this purple line seems to be about 2 and maybe 2.4 squares tall. So I'm going to go up 2.4 squares. Oops. I'm going to go up 2.4 squares from where the weight is attached to the string. So here's one, here's two, and here's zero point 0.4. So roughly like that. Now, if I complete the parallelogram rule, that would mean this green one is supposed to be parallel to this one. I know it's not exactly, but I'm trying to draw it that way. And then this, let's say this blue one is supposed to be parallel to this red one right here. Again, it might not be. But if that is the case, then we would have an equilibrium situation. So in order to make that so, what I'm going to do now is change my vector like this. And what we'd see now is that the parallelogram rule applied to the two red tensions, if they have a diagonal across that parallelogram that is exactly equal in magnitude but opposite in direction of the weight mg, then it is an equilibrium, and that's the case. So, as we can see, when the two sides are more specifically when Phil Physics hangs dead center in the on the clothesline, the two tensions are at exactly the same angle, and because they're at the same angle, they have to be equal in magnitude and equal in direction, of course. So that means the tensions would be the same. If, however, that Phil Physics had happened to hang from the clothesline at a different location so that it wasn't centered, then the angle between the vertical and the rope in each case would be quite different. So let me show you another instance of that. I'm going to start off with drawing the clothesline perfectly level like that. Again, here's my pole that's holding the clothesline. That's the horizontal pole, and then again you'd have the vertical one. But now let's imagine that Phil Physics hangs from this particular part, and let's imagine that the weight is a vector that is only two squares long, so that's weight equals mg. Now we can go ahead and take our rope as if it's coming from that to this end of the clothesline. The program drawing it neater was a bit of a problem there, but now I fixed it. And now I'm going to draw another clothesline coming from Phil Physics to there he goes again, to the clothesline hanger. So it's going to be like that. And this time you can see that if I wanted to compare this to vertical, then this angle might be, for instance, let's actually, there it goes again, trying to make that perfect drawing, but not knowing what I want, so it can't do it. That looks a little further than 45 degrees. Let's say that's 48 degrees. And then maybe this one looks more like it might be 80 degrees or so. So I'm going to say this angle right here might be 80 degrees. And that's just me estimating. And it doesn't even matter. We're not using the numbers at all. The 72 was made up, the 48's made up, the 80's made up. The main thing is that you see that the tensions, which have to be parallel to the actual rope. That's why I made the point in the previous question that tensions not only are always stretching objects, but they're also acting only parallel to objects. So the tension this time happens to be again in the actual clothesline, but in this case, the two clotheslines are at significantly different angles. So what I have to do is find a way to figure out exactly what force is acting on the left one and what force is acting on the right one, and just see if they're basically the same length. So all I have to do is go up from the top of the weight vector and draw another vector, the equilibriant. So in this case, I'm going to draw the equilibriant in purple. And since it was two squares long, I know the equilibriant should be that force. That's the equilibrium specifically for that force. So what we need now is two tensions that add up to give us that equilibrium. And we know the rule for adding vectors that aren't parallel. Obviously, when they are parallel, you just add the magnitudes. When they're anti-parallel, you subtract the magnitudes, and the one with the biggest magnitude wins the direction war. But when they're at angles other than parallel and anti-parallel, we have to use the parallelogram rule. So in this case, we're going to draw a side that is parallel to the right rope. So I'm going to take and try to draw a line from the top of the equilibrium to the rope on the left that happens to be parallel to the rope on the right. So that looks pretty close to being parallel. If I really wanted it parallel, I could try maybe click on this and then make a copy and paste sort of scenario. But let's see if it's, yeah, it will. Copy, paste. Okay, so now that I have that, I can actually move this around and make sure that I am actually acting parallel. So that really should be the direction that it acts at. We can see that it's not quite exactly right when I did it, when I did the green one, but it's pretty close. Now I need another force that's exactly parallel to this one. are exactly parallel to this rope, and I'm trying to click on it to make it come up, but it's not doing it. So I'm just going to wing it again, and using my green marker, I'm going to try to draw a line parallel to this one, to the tension on the left. And that looks pretty good. Now, if you want to look at that, now you can figure out exactly which tension is larger by comparing the length of this tension to this tension, like this. So this tension left and this is tension right, and they do add up to an equilibrium, to a sum that is equal to the equilibrium for the weight. And in fact, we see that TL is greater than TR. So that's how we could actually address the question. When field physics hangs at rest in the middle of the clothesline, the tension will not be the same in each side of the rope when, uh, specifically, when the angles of the two ropes are different. Okay, or the directions of the two tensions are different. That's another way of saying it. So that is what happens when fill physics hangs from a clothesline, but not in the center, rather on the edge. And there's a useful trend here. We see that the line that's closer to vertical is more likely to carry the larger portion, because we see the tension in the left rope points a lot closer to vertical. It's only 48 degrees from vertical, whereas the one on the right is more like 80 degrees from vertical, and it's shorter. So that's another general trend we'll see whenever you have two ropes at different angles holding up a person or an object or whatever. So hopefully that question helps. Let's look at the next question. What types of objects are subject to the equilibrium rule? This again is an open-ended question, but the main point is the equilibrium rule is this. Is the summation of all the forces acting on an object or a system is equal to zero. And when that's the case, then if the summation of the forces is equal to zero, then the object slash system, because it could be several objects that you're applying Newton's laws of motion to, then the object slash system on which those forces act will be in uniform motion. Uniform motion implies that its velocity is a constant. So v equals a constant vector, which is called dynamic equilibrium, unless v equals zero. If v equals zero, then it's in static equilibrium. That's what your textbook author is calling this. Now, there's a lot of people that use this terminology, but I will say that not everybody tends to call it dynamic equilibrium when an object's moving at constant velocity in a fixed direction. But that is the choice that your author's choosing, and I suspect everybody recognizes what it means if someone says that. So just be advised that there might be other terms that you'll run into. But the main thing is the net force equals zero is applied to objects that are in dynamic equilibrium and objects that are in static equilibrium. So let's look at another one. When Brian and Billy, Brian's my brother, by the way, and I'm Billy. When Brian and Billy stand on opposite ends of a scaffold used for installing cedar shake siding, the tensions in the supporting ropes do what? So I'm going to draw a scaffolding right about there. And what we're imagining is that there is a rope here and that there's another rope here, and that me and my brother Brian are standing on opposite sides. If we actually work it very precisely so that me and my brother are literally mirror images of each other, and we're standing in exactly the same positions relative to the ropes, then we could say Billy's weight would point this way, and this would be weight Billy. And again, if my brother stood the same place, again, notice it's exactly the same place. And notice I've also drawn the vectors the exact same length. So in that case, by symmetry, we can again imagine replacing the right-hand side with a mirror dead center on it, and then I look in the mirror, and the right-hand side would look just like the left-hand side. So the tensions in the rope, T left and T right, would be equal. If W Billy equals W Brian, then T left will equal T right. If, however, it's not like that, it could be, for instance, that my fat brother weighs twice as much as me. So this will be weight Brian sub 2. And we could say that my weight is exactly the same as it is right now, in which case this would be W Billy 2 is equal to W Billy. Now, in that case, even though we still took some time to try to make sure that the two forces, my weight and Brian's weight, are actually acting at the same spot, I didn't try to draw it that particularly, but I'm trying to pretend like it's roughly the same spot. I just had to move it to one side so that I could see it different from the green vector. In this case, however, the tension on Brian's side would be larger than the tension on my side. But in order for it to be equilibrium, we'd still have to have the equilibrium rule apply, and that is the summation of the forces is equal to zero. Now, it's hard to see exactly why Brian not being in the center, Brian having the same weight as, or excuse me, it's not obvious Brian having a much bigger weight than me on this side, and me having a weight on the other side, even when we're in the same locations relative to our nearest ropes. It's not completely obvious why that is the case, but your book makes numerous examples where you can see that it would actually work out that way. If you wanted to actually mathematically show it or physically show it, we'd have to introduce the concept of torque. And torque is like a force it's like a force. It's not technically a force. It has units of force times distance. So it would have units of like Newton meters, for instance. If we introduce that torque, then what we discover is that in addition to the summation of the forces, we would also have to have the summation of the torques is equal to zero. And that's what ultimately dictates that when Brian is heavier than Billy, then the tension on Brian's side would be larger than the tension on Billy's side, which is the right. Uh, so that's another issue to keep in mind. We could also do things where even if Brian and I weighed the same, if Brian was closer to his rope and I was maybe in the center of the plank, then the majority of the weight or the majority of the tension would be on the left rope. So that's another scenario as well. So what we have to have here is the summation of the forces is equal to zero no matter what in order for it to just keep from accelerating or changing its velocity from zero to something other than zero. Or in the case of an object moving at a fixed speed, it would continue moving at that fixed speed in that fixed direction. Anyways, that's what it is. When Brian and Billy stand on opposite ends of the scaffolding used for installing cedar shake siding, the tensions in the supporting ropes are equal if Brian and Billy are have the same weight and are located in sort of the symmetric positions. If we had the same weight and we're not in symmetric positions, the ropes would be in different tensions. And if we were different weights and in symmetric positions, the tensions would not be the same either. So that's just something to keep in mind. And that's it. I hope this was helpful. In seeing a couple of these examples, I think you'll see these are very much like some of the questions you run into on our practice tests. So keep on plugging along, and hopefully this will help you. Have a good day. Bye bye.